Section 3.3, Rates of Change and Behavior of Graphs. In this section, we are going to focus on two things, two big things. One is the average rate of change, which we have right here. The average rate of change is the change in output divided by the change in input, also notated as delta y over delta x, or you may have seen y2 minus y1 over x2 minus x1, but I prefer this notation here, f of x2 minus f of x1 divided by x2 minus x1. Okay, that's the one big topic. The other is going to be local and absolute extrema of graphs, which are just highest and lowest points, minimums and maximums, and we'll deal with that once we get there. But we want to hold on to this formula for a minute. So the rate of change describes how a quantity changes relative to its input, so that how the output changes compared to its input. The units on a rate of change are output units per input units. Output divided by input as far as our units go. The average rate of change between two input values is the total change in the function values, the outputs, divided by the change in the input values. So we have this table here. We want to find the average rate of change of the price of gasoline between 2007 and 2009. So we have 2 points here, 2007 and 2009. So the way I'm going to write this is my rate of change. I'm going to use m for that because we often use that with linear functions. M is the output, okay, so C of 2009, that's our function name, minus C of 2007 divided by 2009 minus 2007. So the output values at those 2 years divided by the change in the input value. So change in output divided by change in input. So C of 2009 is 241. C of 2007, the cost then is $2.84 divided by 2009 minus 2007. All right, now the denominator is 2. Our numerator, double check my arithmetic, negative 0.43, which means our rate of change is negative 0.215. Negative 0.215. Now, we want units here. Okay, the output units divided by the input units. So we have cost per year. We have these are all costs, and we have change in years. So this is negative $0.215 per year. So it looks like the cost of gasoline, according to this data, has gone down 22 cents a year between 2007 and 2009. Now that does not say anything about the rest of our table. That just says between those 2 years, that's how it has changed per year. Example 2, given the function g of t in the figure here, find the average rate of change on the interval negative 1 to 2. All right, well, as we wrote earlier in that formula, I'm going to find f of 2, which in this case it's actually g, so let me call it that. So g of 2 minus g of negative 1 divided by 2 minus negative 1. Finding points on here, at an input value of 2, we have an output of negative 1. So this is negative 1 minus, and at negative 1, we have an output of 4, it looks like, divided by 2 minus negative 1. So our average rate of change is negative 5. Hold on. Oh, that's positive 1. Why did I write negative 1? Alright, let's make that Let's make that -3 divided by +3 or -1. So our rate of change, our average rate of change is -1 between those 2 points. One way to envision what this looks like is if I connected these 2 points. That is actually the slope. -1 is the slope of that line. You can kind of see it decreases 3 and then goes to the right 3. That's where our average rate of change is coming in. All right, number 3. After picking up a friend who lives 10 miles away and leaving on a trip, Anna records her distance from home over time. The values are shown in the table below. Find her average speed over the first 6 hours. So for the first 6 hours, the points we are looking at are from here to here, from time 0 to time 6. All right. Our change, our rate of change, is going to be d of, the function is d. So d of 6 minus d of 0 divided by 6 minus 0. So change in the outputs divided by the change in the inputs. D of 6 is 292. D of 0 is 10. And we have 6 minus 0. So this puts us at 282 divided by 6. Now 282 divided by 6 is 47. So what it looks like we have here is 47 miles per hour. That is her speed. She's going 47 miles per hour after she picks her friend up. Example 4, compute the average rate of change of f of x equals x squared minus 1 over x on the interval 2 to 4. So again, m equals f of 4 minus f of 2 divided by 4 minus 2. Now f of 4, we'll find that out over here. That is 4 squared minus 1/4. 16 minus 1/4, which is 63 fourths. Because 16 is 64 over 4. Okay. Make all that connect. And then f of 2 is 2 squared minus 1/2. So 4 minus 1/2 would be 7 over 2, or 3 1/2. So this is 63 over 4 minus 7 over 2 divided by 2. 63 fourths minus 7 over 2 is 49 fourths divided by 2, which is 49 eighths. All right, 49 eighths. And that is our average rate of change. All right, example 5, the electrostatic force F, measured in newtons, between two charged particles can be related to the distance between the particles d in centimeters by the formula F of d equals 2 divided by d squared. Find the average rate of change of force if the distance between the particles is increased from 2 to 6 centimeters. So we have capital F of 6. And by the way, you might notice I have used the second point minus the first point every time. It does not matter. You can use the first and the second. It's just a preference, a personal preference there. So evaluating the force function at 6, that is 2/36, also known as 1/18. F of 2 is 2/4 or 1/2, divided by, and I'll go ahead and simplify that to be 4. Alright, 2/36 minus 2/4, so 1/18 minus 1/2 is negative 4/9. Negative 4/9, and then we'll divide that by 4 to be negative 1/9. So that is negative 1/9, and our unit of output is newtons, divided by our unit of input, which is centimeters, so newtons per centimeter. Example 6, find the average rate of change of g of t equals t squared plus 3t plus 1 over the interval 0 to a. Now this is going to be in terms of a. Okay, we're not going to have a numerical answer. So this will be g of a minus g of 0 divided by a minus 0. Oops. A minus 0 there. Evaluating at a, that is t squared plus, how about a squared? A squared plus 3a plus 1 minus, evaluating that at 0, that is simply 1 divided by a. So that simplifies to a squared plus 3a divided by a. Factoring an a out and canceling, we find that our average rate of change is a plus 3. Of course, that is in terms of a. All right, that is the breaking point. Now, the next thing we're going to talk about, next concept, is the idea of a local minimum and a local maximum. Now, this definition can be overwhelming. It has a whole lot in it, a whole lot going on, but keep in mind that a minimum and a maximum just mean the highest and the lowest point. Okay, the minimum is the lowest point, the maximum is the highest point. So we have two things here. One is an increasing versus a decreasing function. If a function is getting larger over time, then it's increasing, going from left to right. And it is decreasing if our outputs are decreasing. They're going down as we go from left to right. Now, a local maximum exists if in a certain region it's that the function, the output values are larger than its surrounding area. Okay, so a maximum is we've got our function here and here, and at this point it is higher. The output value is larger than the surrounding area, whereas a minimum, something like this. Our function is larger around that point. It's lower at that point. Okay, that's kind of what we're looking for. So let's actually just look at this graph. You can come back to the definition if you'd like. Given the function, given the function, identify the intervals on which the function appears to be increasing. Well, it appears to be increasing from here to here, and from here to infinity. So the way I'm going to write that in interval notation is from 1 to 3, those are my input values, 1 to 3, union, and we'll include 4, but obviously not include infinity. Function is increasing between 1 and 3, and from 4 to infinity. Example 8, graph the function f of x equals 2 over x plus x over 3. Then use the graph to estimate the local extrema of the function and determine the intervals in which the function is increasing. Well, there's the graph right there. Now, I have gone ahead and inserted some images of what I've done on my calculator. So I'll try to explain as I'm going. But first, if you notice, the highest point there appears to be somewhere around here. And the lowest point, going on the right branch, lowest point appears to be somewhere around there. Looks like 2.5, positive 2.5 and negative 2.5. Okay, here is on my TI, is it 83 I've got? Yeah, 83 Silver Edition. Okay, so what you do is you use the function, let's say second calc, not parentheses there, second calc, and then we select maximum or minimum, depending on what you're looking at. So you might inspect the graph first, determine what you're looking for. When I selected my maximum, it gives me this value, negative 2.44949. And when I search for a minimum, I have this. Now the x value is where my minimum occurs. The actual minimum is 1.63299932. That is the actual value, so that's the y value. But the x coordinate is what I'm actually looking at. Where is the local minimum or maximum? All right, so it appears on this graph at first glance to be negative 2.5 and positive 2.5, but it is actually negative 2.44. I'll go ahead and round it to negative 2.45. All right, we have a minimum at negative 2.45, and then my output there, oh, that's the maximum, negative 1.63. Let's go ahead and just change that to maximum. And we have a minimum, and this is, by the way, called a local maximum. A local maximum because in a certain area, it's the highest point. And a local minimum is at approximately 2.45, 1.63. Now, the intervals where it is increasing, okay, based off of that, it's increasing from negative infinity up to negative 2.45, and then it begins decreasing. And then it's also decreasing past 0, but it begins to increase again at 2.45 and continues that way towards positive infinity. All right, number 9. We want to find the local extrema, local maximum and local minimum from this graph. All right, now we have the couple of points. A maximum is occurring right here. Okay, that's the highest point in the area of 1. So we have a max at 1, 2. And it appears that we have a minimum. Okay, and let's actually say this differently. We have a maximum. We have a maximum of 2 at x equals 1. Okay, and we have a minimum of the lowest value is negative 2 at x equals, x equals negative 1, which is the point negative 1, negative 2. All right, now an absolute maximum simply means that on the entire domain it's the highest or the lowest point. On this last example, There is no absolute highest or lowest because the function keeps increasing this way and it keeps decreasing this way. However, on something like this next graph, we can find absolute maximum and absolute minimum. The absolute highest point, the highest value is right here at, it looks like 16, and there are actually two places. Okay, a maximum of 16 at x equals, that occurs at x equals -2 and x equals +2. Okay, that is the point -2, 16 and the point 2, 16. And we have a minimum, and let me go ahead and say absolute maximum and absolute minimum. The absolute lowest point here is this one right here. It appears to be -10. Minimum of -10 at x equals 3, which corresponds to the point 3, -10. All right, that brings us to the end of this section. Okay, rate of change, we have that. Make sure you keep that equation at the very beginning. That is important. We have the change in outputs divided by the change in inputs. And then we have this idea of maximums and minimums. Extrema is what we call those in general. Highest and lowest points respectively. Keep that in mind.